In example 1 and 2 on page 13, we've seen and used the idea of right-handed and left-handed limits. Let's define what we mean by that. So left and right hand limits. Hopefully you have a pretty good idea graphically of what we mean. The formal definition is as follows. If f can be made arbitrarily close to L by taking x values sufficiently close to a while always having x less than a, we write the limit as x approaches a from the left of f of x is equal to L. And similarly, if f can be made arbitrarily close to L by taking x values sufficiently close to a by always having x greater than a, we write the limit as x approaches a from the right of f of x is equal to L. So these two limits are called the left and right hand limits of f, respectively. Now the overall limit as x approaches a of f of x exists if and only if both of those other two limits exist, the left and the right-handed limits, and if they are equal to each other. So we can fill in the blank by saying the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x. In the examples that we looked at so far, we've seen different cases that can happen. We saw some cases where the left-hand limit and the right-hand limit were equal to each other, and others where they were not equal to each other. And then we also sometimes saw that the function value agreed with the limit, and sometimes it only agreed with the left-hand limit, and sometimes it only agreed with the right-hand limit, and sometimes it didn't agree at all. So when the left-hand limit and the right-hand limit and the function value all agree at a point, that is pretty special. And that's in what we are going to talk about in this theorem on page 14. So if the graph of f has no breaks or jumps at x equals a, then we can compute the limit as x approaches a of f of x by actually looking at what is going on the graph. So let's draw the graph. Let's draw the picture of what we are talking about here. So we have our x-axis right here, we have our y-axis right here, and let's say we just have some function f of x. So here we have y equals f of x, a function, and somewhere we have a value of a. And no breaks or jumps. That's the type of graph I drew. And so then look what happens right here. We don't have a break, we don't have a jump. We have a point right here that has input a and output f of a. So the output would be somewhere over here on the right. So this is f of a. And in this situation that I've drawn, the limit as x approaches a from the left or from the right is the same. And we see that it's also equal to the function value. And so in this case, we can compute the limit by simply evaluating the function at a. So if our function is sufficiently well behaved, and by that we mean no breaks, no jumps, at x equals a, then we can compute the limit as x approaches a of f of x by just computing f of a.